Okay, let's talk about the geometry of linear maps. This begins on page, what's the page number? 289. And I like this section very much because it's very intuitive. It shows you what these linear maps actually does. And remember, a linear map is associated with a matrix. So whenever you apply a matrix to vectors, it transforms those vectors. And this section shows you geometrically what happens to the vectors when you multiply them by a matrix. Okay, so by comparison, let's see what happens to elements that are acted on by a nonlinear map. Okay, and let's start with the simplest case. Let's take a nonlinear function of the real numbers. So here we have f1 of x equals e to the x. All right, that's one example. That's the example on the left here. Now, this is operating on the variable x. X is a real number. That's a one-dimensional vector space. So we're looking at a very simple case. And again, this is a nonlinear function, which we'll contrast to the action of linear functions. So what happens when you take e to the x? Well, we can take some specific values. For instance, you can take minus 1. Let's just take minus 1, 0, and 1. If I take minus 1, I get e to the minus 1. If I take 0, I get e to the 0, which is 1. If I take 1, which is e to the 1, which is something like 3. So in this picture, they're showing the domain vector. As I said, I can consider this as a one-dimensional vector. And the image vector. So let's go through this one by one. Minus 1 in the domain goes to e to the minus 1. That's about equal to 1/3. And you can see that here if we start with minus 1, we're coming into something that's less than 1 over here. It's about 1/3. Okay. If I start with x equals 0, it goes to 1. So 0 goes to 1 over here. That looks good. And if I take e to the 1, that's about 3. So it goes up to here to about 3. Now notice how irregular these arrows are. They're not parallel. They seem to be pointing every which way. The situation is even worse when I take f of x equals x squared. I'm not going to analyze this in detail, but just to understand this diagram, if I take f of x equals x squared, if I take x equal minus 2, well, f of minus 2 equals 4. So here I have minus 2 going up to 4. On the other hand, f of 2 equals 4, so I also have 2 going to 4. So this map has a real jumble of arrows going every which way. Now let's contrast this to two linear maps on the real numbers, h of x equals 2x and h2 of x equals minus x. Well, h1 of x, look at this pretty picture, how it just sort of stretches the real line. And when everything is multiplied by 2, 0 goes to 0, 1 goes to 2, 2 goes to 4. You're just stretching everything out and making the gaps larger. On the other hand, if you multiply by something negative, you're also doing kind of an inversion. You're crossing, the positive goes to negative, negative goes to positive. But still, it looks like you can see a very simple pattern here. Now, if I had h2 of x equals minus 2x, I would have both the reflection and the stretching. But you'd still see this kind of very regular pattern. So it makes the point here. The nonlinear map distorts the domain. So the linear maps are more regular. And at each map, all the domain spreads by the same factor. Okay. All right, so the only linear maps from R to R are multiplication by a scalar. So we've considered all possible cases for a one-dimensional vector space. But in higher dimensions, other things can happen. For instance, consider this linear transformation. When we rotate vectors counterclockwise. We've seen that rotation is a linear transformation, and it's associated with a matrix cos theta minus sine theta, cos theta. So if I take vectors in R2 and multiply by that matrix cos theta minus sine theta, cos theta, I get rotated vectors. And you can see no matter what vector I took over here, if I took this vector here, that would rotate down here. Okay, if I took this vector here, it would rotate up here, and it would still be perpendicular to this vector, and so on. Another possibility in 2 dimensions is a projection. If you have this vector in 3-dimensional space, this is intended to be a 3-dimensional vector pointing out from 0. So imagine a line going down here, and this is parallel to the y-axis. This is parallel to the x-axis. So this point here has non-zero x, y, and z coordinates. You arrive at this point by going out x, out y, and up z. However, when I do the projection on the xz plane, just to be clear, this is the x-axis, y-axis, and z-axis. When I do the projection on the xz plane, this smashes down into this plane here. And not just this vector, but any vector along this line, which is parallel to the zy plane, anything along this line, will smash down to the same point. Okay, so there are different varieties of linear maps in higher dimensions. Now, despite this variety, you still have a very simple behavior of these linear maps. And what we want to do is find, in a more general way, what are the possible behaviors of linear maps. And we can do this using Gaussian elimination, okay, what I should say is reduced row echelon form. Now, we talked about how any matrix H can be written as PBQ, where P and Q are non-singular, and B is a partial identity matrix. What does partial identity matrix mean? B has ones on diagonal. Everything off the diagonal is 0. It has ones on the diagonal, but it may also have some zeros on the diagonal. So this is a partial identity matrix. In fact, if H itself is non-singular, then we know that H is row equivalent to the identity, and this matrix B would be the identity matrix. Okay, but given this representation of H as a non-singular matrix times a partial identity, such as the matrix over here, times another non-singular matrix, we can decompose this P and this Q into elementary matrices, which correspond to elementary row operations. So I can write arbitrary H as a sequence of elementary matrices times a partial identity times another sequence of elementary matrices. Okay? And in order to characterize geometrically what linear maps do, I can get there by characterizing geometrically what the different types of elementary matrices do. Okay. Each one of these elementary matrices can be considered as a geometrical transformation. So expressing H as a product of elementary matrices is tantamount to expressing the transformation for H as a series of geometrical transformations on the matrices. So let's go ahead and characterize the geometrical effects of the different elementary matrices. Now you may remember that there are 3 kinds of elementary matrices. There's the kind that multiplies a row by a scalar. There's a kind that switches 2 rows. And there's a kind that takes 1 row and adds to it a multiple of another row. And these are the notations we use for those 3 types of elementary matrices. Okay, so as he says here, if we understand the geometrical effect of a linear map described by a partial identity matrix and the effect of the linear maps described by elementary matrices, then in some sense we'll completely understand the effect of any linear map. Okay. Okay. So first of all, consider the partial identity matrix. Here's a partial identity matrix. If I apply this partial identity matrix to a vector, all that it's going to do is it will leave some components the same, and it will zero out other components. In this case, I had 1, 1, 0. That will only zero out the last component. Okay, and that's general for any type of partial identity matrix. It just depends on the number of components that you'll zero out. Okay, it's hard to imagine 4, 5, 6 dimensions, but from the three-dimensional example, you can kind of see what will happen in those cases. You're just going to smash down the entire space into a lower dimensional space. All right, so that takes care of the partial identity matrices B. Now let's consider the MI matrices. These are the matrices where you multiply one row of the matrix by a constant. And here's an example. This xy goes to 3xy. That's the same thing as multiplying by the matrix 3, 0, 1, 0, 0, 1, which corresponds to, I could call this M1 of 3, because I'm multiplying row 1 by 3. And what this does is it takes the x component and stretches it by 3 and leaves all the other components the same. So you're just stretching along one dimension, in this case the x-axis. And that will be the case no matter what type of MIK you have. MIK will stretch by a factor of k along the ith dimension. Okay? So in 3 dimensions you could think of the same thing. M6 of 2 would be stretching the vectors by a factor of 6 along the y-axis. Or M minus 2 of 3, M3 of minus 2 would be stretching the z-axis by minus, what did I say, minus 2? Okay, and it would look, with respect to the z-axis, it would look something like this picture here. But the other axes would remain the same. All right, so he shows here also a case where you have a negative. In this case, the x's goes to a negative here. If I had a vector along the x-axis, it would end up going along the x-axis in the negative direction. If I have a vector in between these two, then it's going to end up stretching. It's going to be the same height. It will be the same height as this one. Right? I could draw a dotted line across here and it would be the same height. But the x component is being multiplied by minus 2. This type of map is called a dilation. Okay? And you may have seen this in your geometry class. Okay? Transformation represented by the Pij. Remember, Pij is row exchange. So we interchange the ith and jth rows. Now, in this simple example of 2 dimensions, if I exchange the x and the y, going to y and x, then I'm going to be changing the x to the y and the y to the x. And if you do plot a couple of points like this, you'll see that you're taking vectors, and the result of the map takes the vector to its mirror image, assuming the mirror is along the 45-degree line. So in 2 dimensions, you can see how this works. It's just reflection around the 45-degree line. If I took a vector like this, it would reflect to a vector, actually it would reflect to a vector up here. Okay. Now you might wonder how this works out in higher dimensions. In higher dimensions, this would be reflection around, not around a line, but around a hyperplane. Okay. Okay. As you know, in 3 dimensions, a mirror is 2-dimensional. So in 4 dimensions, a mirror would be 3-dimensional. But still, I can characterize this type of mapping as a reflection in a 45-degree hyperplane in whatever vector space I'm working in. Okay. Now, the last type of elementary matrix takes k times row I and adds to row j. So let's look geometrically at what this does to vectors in R2. All right, so in this case, C12 of 2 would be take row 1, multiply by 2, and add to row 2. If I do that operation on the identity matrix, I obtain this matrix here, 1, 0, 2, 1. Right? This is the same thing as taking row 1 of the identity matrix, which is 1, 0, multiplying by 2, and adding to row 2. And this is my result. And we know that to accomplish an elementary row operation, it's the same thing as multiplying by this matrix, which is obtained by the row operation on the identity. Okay? So if I apply this matrix to this vector here, you can work out that this is the result. X remains the same, the y component changes. And then you can plot the result of this mapping on different vectors. Now, it's useful to characterize this map is see what it does to a square. All right? So if you plot this square, and you think about what happens to points in this square, you could plot several points in this square, you'll see that what happens to the square is the x height of the square is not changed, it's just sort of slid up. And the y height, the different, how can I say, the different slices here parallel to the y-axis get moved up the y-axis. You can plot different forms points and verify this. For instance, if I have 1, 0 is going to go to 1, 2. That means that this point here maps to this point here. If I have 1, 1, it's going to go to 1, 3, so this point here maps to this point here. So in effect, this entire square will get mapped to this rhombus. You know, a rhombus is a parallelogram with equal sides. So it's kind of been, well, I don't know how you would describe it. Mathematically, this is called a shear. And you can kind of see that's what happens when you shear something. It's when you shear off, you're moving it sideways. You're moving this thing sideways. Okay. If we had the shear along the parallel to the x-axis, we get a result like this. Okay. Now, the upshot of this whole thing is that in order to understand the effect of a matrix acting on vectors, if I can write that matrix as a product of elementary operations, then each one of these elementary operations corresponds to one of these linear transformations. So I can geometrically represent what each transformation does to a vector and see the result. So for instance, if I took this transformation and then followed that by a reflection, then this here, let me get these points here. Okay. Remember, this was 0, 0. This point was, I think it's 1, 2. And this point is 1, 3. Now, if I followed this by a reflection, and the reflection takes x, y to y, x, well, sorry. Then what would the parallelogram look like? Well, it wouldn't look like this. It would actually end up looking more like this, because I'm taking that parallelogram and I'm rotating it around the 45-degree line. Right? This parallelogram that goes up here would end up reflecting to a parallelogram that goes down here. And in fact, I would get exactly this result here. Okay. And you can see also that if I take this shear and follow by this reflection, I end up exactly with this transformation. Okay. So when you do homework problems here, let's look at these homework problems here. Here, for instance, it says for the clockwise rotation by pi or 4 radians, you want to find its matrix, you want to express it, you want to row reduce, and when you row reduce, you're going to find this sequence of elementary matrices. Now, using these elementary matrices, you can find a solution for H, and you can write H as a combination of mappings. So you can write a sequence of maps. You should start with a square, and then take how that maps, and then show where the square maps to. I don't know, it might map over here, and then show where the square maps to. It might do a stretching. It might stretch everything by 2, which would be something like this. Okay, and so on. Okay, so that's how you can do these problems. Right? I'm not going to talk more about this section, but you're welcome to read more. It's a very good section that gives a lot of intuition and ties a lot of concepts together.